In this lecture, we are going to discuss about two important theorems of integral calculus. One is fundamental theorem of integral calculus and mean value theorem of integral calculus. In the earlier class, we have defined upper and lower Riemann sums. Suppose if f is any bounded function on a closed interval a b, then it is bounded on each of its subintervals x1, x2, x2, x3, so on xn minus 1 comma xn, or in fact it is bounded on general rth subinterval xr minus 1 comma xr for r is equal to 1 to n. We know that the sum m1 delta 1 plus small m2 delta 2 so on mr delta r, which is sigma r is equal to 1 to n small mr delta r, is known as the lower Riemann sum or lower Darboux sum, and the sum capital M1 delta 1 plus capital M2 delta 2 so on mr delta r, which is equal to sigma r is equal to 1 to n capital mr delta r. This is known as upper Riemann sum or upper Darboux sum corresponding to the partition P, and it is denoted by UPF. And in the previous lesson, we have seen that set of all UPF is bounded below, and the set of all LPF for finitely many partitions of AB, it is bounded above. So, the lower Riemann integral, we defined it as supremum of LPF for P belongs to partitions of AB, which is denoted by lower integral a to b f of x dx. The upper Riemann integral of f on AB is defined as infimum of UPF, and we defined the Riemann integral if and only if, or f is Riemann integrable on AB if and only if lower integral a to b f of x dx is equal to upper integral a to b f of x dx, and its common value is integral a to b f of x dx. Suppose for example, we know that any constant function is integrable. How we prove? Here suppose f is a constant function, means for all x belongs to closed interval a b, f of x is k. That means small m, that means infimum and supremum of f are k only. So, what is our UPF? It is sigma r is equal to 1 to n, r is equal to 1 to n mr delta r, or we can take sigma I is equal to 1 to n mi delta I, which is k into b minus a, and LPF is also k into b minus a. Here lower integral a to b f of x dx is supremum of LPF, which is nothing but k into b minus a, and upper integral a to b f of x dx is equal to infimum of UPF, which is also equal to k into b minus a. Here we can clearly see that lower integral a to b f of x dx is equal to upper integral a to b f of x dx, both are equal and their common value is k into b minus a. Therefore, any constant function is Riemann integrable. And also suppose you are given any function f of x equal to x square. How you compute UPF and LPF? Or upper integral 0 to a f of x dx and lower integral 0 to a f of x dx. We have to take the partition P is equal to 0, a by n, 2a by n, and so on na by n. It is a partition. Now, for any interval how you take IR? It is xr minus 1 comma xr. So, this is r minus 1 into a by n comma ra by n for r is equal to 1 to n. Now, how you compute capital MR? Capital MR, here f of x is x square. So, capital MR is r square a square by n square, and small mr is r minus 1 whole square into a square by n square. Now, what is the delta r? Delta r is length of the each interval, which is given by a by n. Now, what is UPF? UPF is sigma r is equal to 1 to n capital MR delta r, which is nothing but a square by n square into sigma r is equal to 1 to n r square. We know that sum of the squares of first n natural numbers is nothing but n into n plus 1 into 2n plus 1 by 6. So, our UPF value is nothing but a cube into a cube by n cube into n plus 1 into 2n plus 1 by 6. Now, you have to find the upper integral 0 to a f of x dx, that is nothing but limit n tends to infinity infimum of UPF. So, if you find limit n tends to infinity a cube by 6 into n into 2n plus n into n plus 1 into 2n plus 1 by 6 value, that we get it as a cube by 3. In the similar manner, we can compute LPF. We can compute LPF, which is also will be equal to a cube by 3. So, you have the integral, that means the function f of x equal to x square, which is a continuous function. It is integrable on the closed interval 0 comma a, and its value is a cube by 3. Now, every continuous function is Riemann integrable on closed interval a b, and also any monotonic function is also integrable on a b. And if f has finite number of discontinuities on the closed interval a b, then also f is integrable on a b. That means, for this kind of functions, for continuous functions, monotonic functions, and functions having finite number of discontinuities, we have your UPF minus LPF is less than epsilon. Now, we are going to define functions like that means, suppose you see what is integral of cos x, integral of cos x is sin x, that is also a function. So, if you define f of x is equal to sin x, then integral of f of x dx is minus cos x. So, that is why here we are going to study about functions defined by integrals to prove the fundamental theorem of integral calculus, which will give you integration and differentiation or reverse processes. That means, if phi dash x equal to f of x, then integral of f of x dx is phi of b minus phi of a, which is called the fundamental theorem of integral calculus. By using the same, we are solving many definite integrals with the limits. For that, to introduce this one, how you define a function with the help of integral. Suppose f is Riemann integrable on a b. If f is Riemann integrable on a b, we write f belongs to R a b. Then the function capital F defined on a b by f of x is equal to integral a to x f of t dt, which is continuous on a b. Further, small f is also continuous at c on a b. Then f is derivable at c, and f dash c is nothing but f of c. So, we prove that the function capital F of x, which is defined in the form of integral given by integral a to x f of t dt, it is a continuous function and it is having a derivative also. With the help of this theorem, we are going to define primitive of a function f. Suppose f belongs to R a b, that means f is Riemann integrable on a b. What does it follow? Every Riemann integrable function is bounded on a b. What do you mean by, or when you say that a function is bounded? When mod f of x is less than some real number k. That means, whenever you have f is bounded on a b, mod f is also bounded on a b. Let capital M be the supremum of mod f. Then choose a delta such that 0 less than delta less than epsilon by m. Why we are taking this? What do you mean by the function small f is continuous? We say that function f is continuous at c if limit extends to c f of x equal to f of c. That means, for given epsilon greater than 0, there exists a delta greater than 0 such that mod f of x minus f of c is less than epsilon whenever 0 less than mod x minus a is less than delta. So, for that now we prove that, making use of this continuity concept of small f, we prove that capital F is continuous. If you want to prove capital F is continuous, it is required to prove mod f of x plus h minus f of x is less than epsilon. For that, what is mod f of capital F of x plus h minus f of x? It is modulus of integral a to x plus h f of t dt minus integral a to x f of t dt. Why? Because we have defined f of x equal to, integral a to x f of t dt. So, you simplify that, that is integral a to x plus h f of t dt, that this minus integral a to x, here you see minus integral a to x f of t dt can be written as plus integral x to a f of t dt. That means, you will get integral a to a, you have, see here, integral x to x plus h f of t dt. That means, you have, this is modulus of integral x to x plus h f of t dt, which is less than or equal to m into mod h, which is less than m into delta, that is less than epsilon, because we have chosen that delta in such a way that here we have chosen delta such that delta is less than epsilon by capital M, and we are saying that capital M is the supremum of f, means mod f is less than m. So, here let f be continuous at C belongs to A B. Then for given epsilon greater than 0, there exists a delta greater than 0 such that mod, whenever mod t minus c is less than delta, we have mod f of t minus f of c is less than epsilon. So, what do you mean by that? F of c plus h minus f of c by h minus f of c, which is equal to 1 by h into f of c plus h minus f of c minus h into f dash c. You take like this, consider this one. Actually, here we got mod f of x, capital F of x plus h minus f of x. After simplification, we got this is less than epsilon, which shows that capital F is continuous. So, when now we proved that capital F is continuous. Now, we prove capital F is differentiable. When do you say that a function capital F is differentiable? We say that the function f is differentiable if limit h tends to 0, f of x plus h minus f of x by h limit exists. For that, we have to consider modulus of f of c plus h minus f of c by h minus f dash c. For this, I prove that limit h tends to 0, capital F of c plus h minus f of c by h is equal to f dash c. For that, I will make use of the definition of f of c plus h, or I will make use of definition of f of t. That means, if you have f of c plus h minus f of c minus h into f dash c, value will be 1 by h into integral c to c plus h f of t minus f of c dt. Now, consider modulus of this, mod f of c plus h minus f of c by h minus f dash c is equal to 1 by mod h into modulus of integral c to c plus h f of t minus f of c dt. We know that integral of modulus integral of f of x is less than or equal to integral of modulus. So, you have this is less than or equal to 1 by mod h into modulus integral c to c plus h mod f of t minus f of c dt, which is less than 1 by mod h into epsilon into mod h, which is epsilon. So, what does it follows? We have capital F is derivable at C and f dash C is equal to f of C. Here we are going to, with the help of this, we are going to define primitive of a function f. If f is Riemann integrable on a b, if there exists a function phi on closed interval a b such that phi dash x equal to f of x. If phi dash x equal to f of x, then phi is called the primitive of f. Phi is called the primitive of f. That is, we have derivative of sin x is cos x, derivative, that is sin x derivative is cos x. So, sin x is the primitive of cos x. Like that we can give many examples. Now, we are going to prove fundamental theorem of integral calculus, which is very important theorem of calculus and which plays a major role in calculus, which states that if f is Riemann integrable on a b and phi is the primitive of f, then integral a to b f of x dx, integral a to b f of x dx is equal to phi of b minus phi of a. This is the statement of fundamental theorem of integral calculus. Now, see here, other than UPF and LPF, or other than using upper Riemann sums and lower Riemann sums, we can define the integral as if a function f is said to be integrable over a b if there exists a number, or if there exists a number I, and for to each epsilon greater than 0 there exists a delta greater than 0, and for every partition p x naught, x1, x2, etc., xn of norm p less than or equal to delta and xi belongs to xr minus 1 comma xr, if modulus of sigma r is equal to 1 to n f of xi r into xr minus 1, that is nothing but delta r. If modulus of sigma r is equal to 1 to n f of xi r delta r minus I is less than epsilon, then we say that f is Riemann, f is integrable, and the number I is called the integral of the function f over the interval a b, and we write I is equal to integral a to b f of x dx. And we can easily prove the definition of two integrals, definitions of two integrals are equivalent. So, we make use of the second definition. We are going to prove the fundamental theorem of integral calculus. Given phi dash x equal to f of x, he told that phi is the primitive of f. That means phi dash x equal to f of x for every x belongs to a b and f belongs to R a b. That means f is Riemann integrable on a b, implies for given epsilon greater than 0 there exists a delta greater than 0 and a partition p of a b with norm p less than delta, such that sigma r is equal to 1 to n f of y r delta r or f of xi r delta r minus I is less than epsilon. I told you I is integral a to b f of x dx. Now, if you consider each xi r lies between x r minus 1 and x r. Okay. Now, phi is differentiable on closed interval a b and it is continuous on closed interval a b. That means phi satisfies all the conditions of Lagrange's mean value theorem. So, here we are making use of fundamental theorem of differential calculus or Lagrange's mean value theorem, which states that if when f is continuous on closed interval a b and f is derivable, then there exists C belongs to open interval a b such that f dash C is equal to f of b minus f of a by b minus a. So, here we apply Lagrange's mean value theorem for the function phi. on the interval xr minus 1 comma xr, that is phi of xr minus phi of xr minus 1 is equal to xr minus 1 into phi dash of xi r or phi dash of y r. Now, take sigma on both sides, you get sigma r is equal to 1 to n phi of x r minus phi of x r minus 1, which is equal to sigma r is equal to 1 to n x r minus 1 into phi dash of y r, that is nothing but sigma r is equal to 1 to n delta r into f of y r. Now, expand this sigma on left hand side. What is the sigma r is equal to 1 to n phi of x r minus phi of x r minus 1, it is phi of x 1 minus phi of x naught plus phi of x 2 minus phi of x 1 plus and so on plus phi of x n minus 1 minus phi of x n. So, these terms phi of x 1 minus phi of x 1 terms will get cancelled, and finally, you are left with phi of x n minus phi of x naught, which is nothing but phi of b minus phi of a. Now, take norm p tends to 0 on both sides, that is limit norm p tends to 0 phi of b minus phi of a is equal to limit norm p tends to 0 sigma r is equal to 1 to n f of y r delta r, which is nothing but integral a to b f of x dx. So, what does it mean? Integral a to b f of x dx is equal to phi of b minus phi of a. This is called the fundamental theorem of integral calculus. So, how you apply? For example, just look into this. Integral 0 to 1 x power 4 into dx equal to x power 4 dx is equal to 1 by 5. Generally, how you solve this sum? We know that integral of x power n dx is x power n plus 1 by n plus 1. So, integral x power 4 is x power 5 by 5. If you apply limits 0 to 1, you get 1 by 5. The same thing we are going to prove by making use of fundamental theorem of integral calculus. You have f of x equal to x power 4, we know that, which is an algebraic function continuous on R. So, it is continuous on 0 1. That means, we know that every continuous function is Riemann integrable. So, integral 0 to 1 x power 4 dx exists. So, you take phi of x as x power 5 by 5. So, that phi dash x equal to f of x. Here you have to choose a function phi such that phi dash x equal to f of x. So, you define phi of x equal to x power 5 by 5 for every x belongs to 0 1. Then phi of x is derivable and phi dash x is f of x. Hence, by fundamental theorem of integral calculus, what 0 to 1 x power 4 dx, it is phi of b minus phi of a, that is phi of 1 minus phi of 0, which is nothing but 1 by 5. And one more example, you check. Using fundamental theorem of integral calculus, evaluate integral 0 to pi by 4 secant power 4x minus tan power 4x dx. First of all, this secant power 4x minus tan power 4x can be written as secant square x whole square minus tan square x whole square, which is of the form a square minus b square, and we write it as a plus b into a minus b. That is secant square x minus tan square x into secant square x plus tan square x. We know that secant square x minus tan square x is 1. So, this secant square x plus tan square x can be written as, you write only in terms of secant square x. We know that tan square x is secant square x minus 1. So, secant square x plus tan square x equal to 2 into secant square x minus 1. So, how you take primitive? You take integral of this one. We know that integral of secant square x is tan x. So, you define phi of x equal to 2 tan x minus x on 0 4. So, that phi dash x is 2 into secant square minus x, 2 into secant square x minus 1. So, here also we got phi dash x equal to f of x, that is phi is the primitive of f. That means, what will be the value of integral 0 to pi by 4 secant power 4 x minus tan power 4 x dx? It is phi of pi by 4 minus phi of 0, that is 2 tan pi by 4, you substitute here 2 tan pi by 4 minus pi by 4 minus 0. What is phi of 0? Phi of 0 is 0. Phi of pi by 4 is 2 tan pi by 4 minus pi by 4. So, you get tan pi by 4 is 1 and you get it as 2 minus pi by 4. Hence, the integral of secant power 4 x minus tan power 4 x under the limits 0 to pi by 4 is 2 minus pi by 4. This is about fundamental theorem of integral calculus. Next, we are going to discuss about the next important theorem of theorem of integral calculus called mean value theorem. Here in the previous lessons or previous classes, we have proved that integral small m into b minus a is less than or equal to integral a to b f of x dx is less than or equal to capital M into b minus a, by making use of the definition of Riemann integrability. So, here mean value theorem of integral calculus states that whenever f is continuous on a b and g is integrable on a b such that g of x is always positive. That means, g of x is greater than 0 for all x belongs to a b, then we say that there exists a point C belongs to a b such that integral a to b f of x gx f of x into g of x dx is equal to f of c into integral a to b g of x dx. So, this is the important mean value theorem which gives the product of f of x and g of x under the limits a to b, that is integral a to b f of x into g of x dx is equal to f of c into integral a to b g of x dx, where f and g are integrable functions. So, here what we can say is whenever f and g are integrable, then their product is also integrable. Product of two integrable functions is integrable. So, let small m be the infimum of f and capital M be the supremum of f on the closed interval a b. Then what we can say, small m into, that means all the values of f lies between small m and capital M, that is small m less than or equal to f of x less than or equal to capital M. You multiply on both sides with g of x, so that the inequality will not change. Why? Because your g of x is always positive. So, you have m into g of x less than or equal to f of x into g of x is less than or equal to capital M into g of x for every x belongs to a b. So, integrate m into integral a to b g of x dx is less than or equal to integral a to b f of x into g of x dx is less than or equal to capital M into integral a to b g of x. If integral a to b g of x dx is 0, then we choose c arbitrarily in a b, otherwise you have small m is less than or equal to integral a to b f of x into g of x dx by integral a to b g of x dx, which is less than or equal to capital M. So, since f is continuous, there exists a point c belongs to a b such that f of c is equal to integral a to b f of x into g of x dx by integral a to b g of x dx. F is continuous on a b, and by taking g of x is equal to 1, we can have that there exists c belongs to a b such that integral a to b f of x dx is equal to f of c into b minus a. This is the mean value theorem of integral calculus. In this lesson we learned the fundamental theorem of integral calculus and mean value theorem of integral calculus with the examples. Thank you.